my classmates and Dr. Rao. Today I will present the results of my thesis. The title of my project is Characterization of the Dynamics and Organization of the endothelin 1, the endothelin A and the angiotensin type 1 receptors using fluorescence correlation spectroscopy functions. First, I will bring you the outline of my presentation, which was the questions that lead to this project, the methods that I use to answer these problems, and our major findings, the significance and our future directions. First, what are the receptors that I'm working with? These receptors belong to the large family of the G protein coupled receptors. These receptors are cell surface receptors, and the membrane dynamics is homogeneous, and it's important to understand the lateral mobility of the receptors, and not only to focus in their binding characteristics and the concentration of the ligands, because having studying the lateral mobility of the receptors gave us insights of the molecular interactions of the receptors and the membrane proteins and membrane lipids that it has. Regarding to the organization of the receptors, at the beginning of the decade, it was thought that the monomers, the receptors organized as monomers, were the receptors that were functional. With the years, it's thought that the dimers and also the higher order aggregates are also functional for G protein coupled receptors. The two receptors that I'm working with are the angiotensin 2 type 1 receptor and the endothelin 1 type A receptor. The binding of the endogenous ligand angiotensin 2 that is part of the renin-angiotensin-aldosterone system is responsible of the blood pressure regulation and the water retention. And in the case of the angiotensin type 1 receptor, these receptors, the binding of the endogenous ligand, endothelin 1, that is a potent vasoconstrictor peptide, lead to several cardiovascular diseases like chronic heart failure, renal diseases, and hypertension. Both receptors lead to hypertension through the contraction of the vascular smooth muscles. So, given this, the hypothesis of my work is that the angiotensin type 1 and the endothelin type A receptors that are organized as monomers are moving slowly and they are restricted in a confined area is due to receptors that are in an active state and that will be blocked by the drugs that are called inverse agonists. To work on this hypothesis, the main goal of this project was study the organization and the dynamics of these AT1 and ETA receptors using fluorescence microscopy. We divided our general objective into, first we wanted to characterize the cell line that we are going to use to measure the dynamics. After, the second objective was to characterize the dynamics, how these receptors were moving, and the influence of the ligand binding. The third objective was to determine the aggregates of these receptors and to see if there was an influence of the ligand binding in the receptor and the receptor ligand complexes. The methods that I used to work on objective 1 was the angiotensin type 1 receptor that was tagged in the C-terminal with the yellow fluorescence protein. We first created a stable cell line using a serial cloning method to have a homogeneous population of the construct and also control the expression level of the receptor. to know which clone we were going to use, we first measured the expression level using fluorescence activated cell sorter, that is FACS analysis. Once we determined which was the expression level of these receptors, we measured their functionality. And the functionality, I measured the intracellular calcium release once it was activated by the endogenous ligand using the calcium bioluminescence assay. And also to evaluate the binding affinities and the concentration of the ligands, we performed the radioligand binding assays. For the next receptor, I used the ETA was tagged N-terminal with the green fluorescence protein, and for the functionality of this receptor, I performed film analysis that I measure the fluorescence lifetime of a calcium indicator, and also I do a calcium bioluminescence assay. Once I have selected the clone that was functional and have good binding properties, we perform the experiment to develop two answers, objective 2 and objective 3. Once these cells were transfected using an Olympus microscope that was set in a TIFF mode, I acquired a stack of images to be able to track to be able to image the dynamics and the organization. The TIFF microscope has the particularity that it only illuminate or excite the fluorescence particles that are near or close to the plasma membrane, that are in the plasma membrane because they are close to the plastic of the cover slip. Once I have my image stacks before and after the exposure of the ligands in time, this data is transferred to the CMSCS software. The CMSCS software is the one that allows me to make the analysis for the dynamics and for the organization. So, for the dynamics, to be able to measure the movement of these receptors, I use the IMSD analysis method. The IMSD method means mean square displacement. I measure in a specific region. The IMSD analysis, I measure the mean square displacement of the particles in time, and with this analysis, we are able to extrapolate the different protein diffusion law. The particles in the cells can move randomly, can be confined, or it can be transiently confined. And once we have the protein diffusion law in the IMSD curve, once the IMSD curve cannot extend anymore, it bends, and it will give us the parameter of the confinement in where the particles are moving. In the IMSD graph, it's not working. It's off. It's auto charge. In the IMSD graph, we are able to obtain once we have the IMSD versus time plots. From this, we perform a fitting process using these equations of the IMSD. From these equations, we are able to obtain the parameters of the molecules that are having a long-range diffusion. This means that the particles are freely diffusing across the membrane. From this equation, also, I am able to obtain the parameters of the confined, the local diffusivity of the molecules in the scale D micron, and the size of this confinement, scale L. From all of this IMSD versus time plot, another parameter that we could obtain from this graph is have an idea of the size of the particles based on the intercept of the graph. For this analysis, we obtained a map of the different models in the cells, and we evaluate in time how this map will change and evaluate the different parameters of the diffusion coefficient, how they will vary across the time and the exposure of the light. To work on objective number 3 and evaluate the aggregation state, we perform the number and brightness analysis method. The number brightness analysis method allows us to identify if the fluorescence intensity that we are imaging are coming from particles that are moving individually or particles that are aggregates. Because in this method, we are able to identify even if the particles are forming aggregates, they will have the same intensity, but the variance will change. And looking at that variance and using the equation of the brightness, we are able to detect how many aggregates I have in my cells. So to distinguish the aggregates, first I need to do a calibration. And for this calibration, I use a fluorescence protein that was only a monomer. So when I transfected this fluorescence protein in the cell to be able to obtain the values of that will correspond to the monomers. Localize that all the monomers in the cells are distributed in the entire cell membrane. Now I'll explain what we obtained from one issue of these methods. So when we characterize the different clones in the FACS analysis, we were able to discriminate the cells that were transfected from the cells that were not transfected. And we observed that the transfected cells, it had 30% of 30% of my cells were transfected. And I performed this FACS analysis from each of the single clones that I selected from the serial dilution. Once I have my expression level, I also evaluate the calcium, the release of intracellular calcium in each one of these clones. And we obtained that for most of my clones, is a concentration dependent increase in the intracellular calcium and I activated with the agonist angiotensin II. From these calcium occurrence assays, we were able to obtain the maximal responses of these clones and also the EC50 concentration. Once we have which clones were functional and their activity, we measure the radioligand binding, the binding properties of these receptors. And from each clone, we observe that these clones have specific binding. In this case, I use telmisartan, that is an antagonist of the angiotensin I receptor. I observe that it has a specific binding for these receptors. And in the A2C12 clone, that is the clones that I selected for the following experiments, we observed that this receptor it has a saturable process. The first part, once we selected the clones, we performed the IMSD analysis. And in the IMSD analysis, how I said before, I have a map of the different models that are present in the cell membrane. And in this case, we observed that the confined diffusion model, that is is represented by the green color, is the predominant mode in these cells. Also, we have a map of the long-range diffusion and a map of the local diffusivity and the confinement zone, the confinement area that these receptors were moving. So once we have the map, this map was evaluated in time, and in time we observed that when we try the angiotensin 2, that is the agonist of the receptor, and losartan, this diffusion's mode did not change after the binding. And we have the confinement diffusions that are predominant in the case of the 81 EYFP receptor after the particles were moving as partial confinement, and a low population was freely diffusing in the membrane. But once I have these modes, we extract the diffusion coefficients value. And from the diffusion coefficients of this receptor for the agonist, angiotensin 2, and the antagonist, for the agonist and the antagonist, we didn't observe significant change in the diffusion coefficient values. The values of the long-range diffusions for these receptors were in the range of 0.01 micrometers squared per second to 0.1. What we observed is that the antagonist, losartan, did significantly decrease the movement of the local diffusion, and also it decreased significantly the size of the confinement regions. For the ETA EGFP receptors, here we also obtain the map of the mode of the diffusions and the map of the long-range diffusion, the local diffusivity, and the confinement zone. In this map, we also said that most of our molecules were diffusing within microdomains, within microdomains in the confinement zone. But when we extract these diffusion models and evaluate it in time, we observe that the confined diffusion model and the free diffusion were similar for this receptor. The proportion of particles that were moving as confined and free were similar. And the diffusion coefficient value, in this case, with the agonist endothelin 1, there was not a significant change in the movement of the long-range diffusion, not in the local diffusivity. But we observe a significant change when we test the antagonist BQ1 through 3. In the antagonist BQ1 through 3, we also observe there is a decrease in the long-range diffusion and a decrease in the local diffusivity of these receptors. So for the aggregates, in the number and brightness analysis, we were able to have a map of the different aggregates that I have in the cells, and we observed that the monomers that represented in the red, the dimers that is green, and the tetramers population were distributed heterogeneously in the cell membrane. And once we evaluate how this percentage were moving when I tried the different agonists or antagonists, we observed that for the agonist, angiotensin 2, there was not change in the aggregates. But when we tried the antagonist, losartan, we see that there is a decrease in the percentage of dimers and an increase of monomers. So there is a relationship between the dimers that were decreasing, and after this, we observed that the percentage of monomers increased. And also for the ETA EGFP cells that we tried with the agonist, endothelin 1, the antagonist, BQ123, and citaxetan, we observed only variations in the dimers that were tested with the Q123. For angiotensin 2 and for cetuxetan, we didn't observe any change in the percentage of the aggregates. Discussion. From my results, I could say that for both receptors, for the 81 EYP and the ETA GFP, the confinement movement are the predominant mode of diffusion. And the fact that the movement of these receptors are confined means that this mode is possible rate-limiting process for the signal transduction of this receptor in the plasma membrane. And also the diffusion coefficient values that we obtain using these techniques, the IMSD and coupled with the TIFF method, were in the same range of the different diffusion coefficient values that were obtained in other G proteins coupled receptors that were measured using different techniques like single particle tracking or fluorescence correlation spectroscopy. What we observed that the antagonists, losartan and BQ, are affecting the local environment of these cells. And how this is affecting it has to be argued because the confinement of the receptor is thought because the molecules are moving within microdomains or interacting with different lipid proteins or with the cytoskeleton that are part of the plasma membrane. So we observe that this type of drugs are affecting the local environment of these cells. Regarding to the N&B method, with this method, we have a new evidence in the aggregates, in the aggregation state, because for the 81 and the ETA receptors, most of the techniques that have been done are described monomers and dimers. And also they described that there was not changes in the aggregation using different techniques as FRET or BRET. The advantage that I have with using this technique, the N&B method, compared to the FRET analysis is that for the non-membrane analysis, we don't need to pick or be cautious to pick a fluorescence tag for our receptors. In the case of FRET analysis, we have to select two fluorescence proteins that are close enough to be able to see if there is transfer in the energy, and to see if there are dimers or monomers. In all this work that have been done, we see that the IMSD method provides a rapid analysis that it could give information, qualitative and quantitative information of the protein diffusion law. And also, in comparison with other techniques as single particle tracking, we are able to measure the dynamics of a pool of molecules in the cells, and we don't need to have like single particles to be able to obtain the diffusion law. The confined mode is the predominant mode, and regarding to the N&B method, this method allows us to identify another aggregation, and to the best of our knowledge, this is the first time that we describe it as a new aggregation state for these receptors. And these aggregates, the dimers and the tetramers, also the monomers, are formed constitutive in the cells because we observed them before the addition of the ligands. Once we measure, they were already there. And the exposure of the antagonist losartan is known also as an inverse agonist. And we observe that this inverse agonist losartan is modified the local environment, or is influencing in the local diffusion and in the aggregates of this receptor. So if this receptor is this compound, this antagonist, is considered an inverse agonist. In the case of BQ123, we are also observing that this compound is affecting the local diffusion of the receptor. So there is a possibility that this is not an antagonist. It will be an inverse agonist. The future work that could be derived from these experiments is in regard to the dynamics of these receptors, to understand better this system, how it's that the cytoskeleton and the lipid wraps are part that constrain the diffusion of the molecule. It will be useful to understand if for this receptor also the cytoskeleton is influencing the low diffusion and the confinement mode of the diffusion. And in the aggregates, it will be useful to not only to focus in the binding of this receptor to see if the ligands will affect the dimers or the monomer, but also see if these aggregates are affecting or have an effect or functional effect in the G proteins or in other proteins effector of the molecule. I would like to thank Dr. Acharya, Dr. Rao, and everyone. Then to INDICASAT, to Synapse for the grants, to the University of California, Irvine, and the LFU, where I performed most of the microscopy experiments, to the University of the Free University of Brussels with the Professor Patrick Valdehagen, where I was able to create a stable cell line, and the University of Acharya that gave us the opportunity to do this PhD. Questions?